Welcome to the Explainer. You know, our coastlines are never still. They're constantly being reshaped by every single wave, every storm. Today, we're going to dive into the incredible science that lets us predict those changes. And we'll be looking at a really powerful tool called Xbeach. Okay, so here's our game plan. First, we're going to ask, why do we even need to model coastlines in the first place? Then, we'll pop the hood and see what makes the Xbeach model tick. After that, we'll look at a real-world test case, see how scientists actually put the model through its paces, and finally, we'll wrap up by talking about why all of this work is so incredibly important. I mean, that is the million-dollar question, isn't it? With our shores constantly eroding and storms seemingly getting more intense, scientists and coastal managers are, well, they're in a race against time. They have to figure out how a beach is going to react not just to the next big storm, but for decades to come. Now, these are not crystal balls. Think of them more like digital laboratories. They're built on the fundamental laws of physics, and they let us simulate that complex dance between the waves, the currents, and the sand. It's really our best window into the possible futures of our coasts. So, let's kick things off with the big picture. What is the fundamental problem that a tool like Xbeach was designed to solve? What are the massive challenges we're trying to get a handle on here? Well, the stakes could not be higher. We're literally talking about protecting homes, businesses, and entire communities from flooding and erosion. It's about figuring out if a multi-million-dollar project to dump tons of new sand on a beach is actually going to work. And, it's about making smart plans for the next 100 years as sea levels continue to rise. All right, so we get why we need these models. Now let's take a look at what's inside this Xbeach engine that makes it such a go-to tool for coastal scientists. Okay, that is the technical definition. Let's break that down. Put simply, Xbeach is a super powerful calculator that solves the physics of how groups of waves, not just single waves, smash into the coast. It tracks the energy, the water movement, and then it predicts how all that chaos is going to stir up and move sand, which of course changes the shape of the beach itself. And as you can see in this diagram, Xbeach isn't just one magic formula. It's more like a chain reaction. It starts by calculating what the waves are doing, which tells it about water levels and currents. That, in turn, tells it how much sand gets moved around. And finally, it updates the shape of the seafloor, and then the whole process starts right over again for the next moment in time. Now, here's what's so cool. Xbeach includes this incredibly rich set of physics. It simulates the dangerous pull of undertow, the powerful, slow sloshing of what are called long waves, and even what happens when sand on a steep underwater slope just gives way in an avalanche. This level of detail is what makes it so good at figuring out what happens right there in the surf zone where all the action is. All this theory is fantastic, but the real test, the real proof, is how a model stacks up against reality. I mean, does it actually work when you feed it real-world data? So, to ground this whole explainer, we're going to follow a really interesting study from the Technical University of Delft. Researchers picked the specific stretch of coast in the Netherlands called Vluchtenberg for one main reason. They had access to incredible, high-frequency survey data, basically a whole series of super detailed maps of the beach and seafloor. And this was the challenge for the model. Over 375 days, the real beach changed. You can see areas where sand was carved away and other spots where it piled up. The big looming question is, can Xbeach actually reproduce this exact pattern? Okay, this is where we get to the heart of the scientific process. Because it's not about just pushing a run button and walking away. It's about careful setup, rigorous testing, and a whole lot of refinement. So, this table shows one of the first big choices a modeler has to make. Do you run it in stationary mode, which is way faster but kind of assumes the waves are constant for an hour at a time? Or do you use the much more intense surf beat mode? It's slower, but it simulates the realistic, messy groups of waves that are absolutely critical for modeling a big storm. And right here is where your mind might just explode a little bit. There are hundreds of parameters you can adjust, things that control friction, how waves break, how sand moves. So a huge part of the job is doing what's called a sensitivity analysis. You have to figure out which of these 150 plus knobs and dials actually matter the most. Just look at this, it's incredible. Each of these colored lines is a different model run where they only changed one single parameter related to the shape of the waves. You can see how dramatically that one little tweak alters the entire predicted shape of the beach. This process of tuning is absolutely vital to get the model to match what's happening at a specific location. But, just eyeballing graphs isn't really good enough for rigorous science. To be truly objective, scientists need a report card for the model. So they use these statistical metrics or skill scores to actually grade how well a prediction matches up with the real-world measurements. This table shows one of those scores, the MSS. Now, here's the simple way to read it. A score of 1 would be a perfect prediction. A score of 0 means the model did no better than just guessing the beach wouldn't change at all. And a negative score? Well, a negative score means the model's prediction was actually worse than doing nothing. It just goes to show you how incredibly challenging it is to get this stuff right. So after all this complex physics, all the parameter tuning, all the number crunching, what's the big takeaway? Why do scientists go through all this trouble? And this, right here, is the heart of it. This is not just some academic exercise. The results from these models directly inform everything from where you should place sand for a beach nourishment project to exactly how high you need to build a seawall to protect a town. These are massive, expensive decisions, and the models provide absolutely essential guidance. But it also shows us something beautiful about science. You see, the Vlugenberg study found the model kept over-predicting erosion on the upper part of the beach, and they wondered why. A key reason? The model didn't include the wind blowing dry sand from the beach back up into the dunes. But see, that's not a failure, that's a discovery. The model showed them a gap in their understanding, and that discovery drives the next wave of research to make the next models even better. And that really leaves us with the final, crucial question that drives this entire field. As our world changes, the forces hitting our coasts are going to change too. The challenge for every coastal scientist and engineer is to make sure these incredible predictive tools don't just keep pace, but that they stay one step ahead of the storm.